Nitrogen is an essential building block of all living things, interwoven in every cell in our bodies. It contributes the majority of the atmosphere we breathe and is critically important to understanding the life and processes of our planet. Key to this understanding are the cycles governing different forms of nitrogen and the regulating factors that alter the amount and type of nitrogen. This lecture will cover the processes that compose the nitrogen cycle, as well as providing an example of an ecosystem and its relationship to nitrogen. First, we will start with the fixation of inert atmospheric nitrogen into biologically available nitrogen, known as nitrogen fixation. Nitrogen-fixing microbes use nitrogenase to split the atmospheric nitrogen molecule in two and add hydrogen atoms to create ammonia. The pH of the cell almost always adds a hydrogen, producing ammonium. Nitrogen fixation has multiple regulators. Biologically available nitrogen must be relatively low compared to other nutrients. Nitrogen fixation is energetically expensive, so relatively high levels of biologically available nitrogen would mean other microbes not using nitrogenase would outcompete the nitrogen fixers. The presence of phosphorus, iron, and other nutrients is important for the success of nitrogen fixers. Oxygen inhibition is critical, as oxygen directly inhibits nitrogenase. pH can also be important, with maximum productivity values found at around a pH of 7. For terrestrial systems, moisture is essential to productivity. And finally, temperature is correlated with higher productivity values, typical for microbial activity. Once ammonium is assimilated into the biomass following nitrogen fixation, there are multiple fates for the nitrogen molecule. Over time, the living biomass will die and become part of the sediment. The organic nitrogen may be sequestered there for a time, and this is a process highly regulated by temperature, pH, nutrient availability, and the presence of oxygen. The nitrogen could become bioavailable through ammonification. This is the process where the organic matter is broken down and transformed into the inorganic ammonium. Now, once this ammonium is available in the environment again, it may be once more assimilated into organic nitrogen, or it could be processed into the atmosphere via volatilization. Volatilization is the conversion of ammonium to ammonia, and this usually occurs during periods of high pH, usually more than 8. This occurs due to the hydrogen atom getting torn away from ammonium. Ammonium can also be adsorbed to the sediment. Ammonium is a cation, or a positively charged molecule, and is attracted to oppositely charged sediments. The effectiveness of sediment to capture cations is known as the cation exchange capacity, or CEC. This process is regulated by multiple variables, one of the most important being salinity, as the higher levels of cations present in seawater compete with ammonium for reaction sites on the sediment particles. Ammonium can also be converted into N2 gas via anammox, or finally, converted to nitrate through nitrification. Nitrification is a two-step process that converts ammonium or ammonia into nitrite in the first step, with the second reaction converting nitrite to nitrate. The presence of oxygen is important to nitrification, as it is an aerobic reaction. A pH of 6.5 to 8 is ideal for nitrifying microbes, while a pH of less than 6 is dominated by fungi, and the process can be less efficient or even incomplete, something we will discuss later. Nitrifying organisms are lithoautotrophs, or organisms that get their electrons and carbon from inorganic sources. So the presence of carbon dioxide is also an important factor. Other factors that regulate nitrification include the presence of the ammonium or ammonia and increasing temperature. As with most reactions, as the temperature goes up, so does the rate of nitrification. Nitrification increases nitrate and lowers oxygen levels, which can have a negative effect on water quality. However, this creates the conditions for denitrification, the conversion of nitrate to multiple different nitrogen forms, mainly associated with nitrogen gas. Denitrifying organisms are typically classified as anaerobic organoheterotrophs, organisms that use organic compounds as a source of electrons and carbon in oxygen-free environments. Therefore, this process requires low oxygen conditions and high carbon inputs. High pH is also important, as low pH and oxygen presence can inhibit nitrogen reductase and interrupt the conversion of nitrate into nitrogen gas, producing nitrous oxide, a potent greenhouse gas. This is a similar issue to nitrification, and the two processes can be visualized as a hole-in-pipe model, where the pipe represents the coupled nitrification-denitrification reaction, and the holes represent the intermediates, nitric or nitrous oxide. Other factors that have an impact on denitrification include salinity, where at least in some cases, increasing salinity has been found to have a negative effect on denitrification. Temperature, where typically the higher the temperature, the higher the denitrification. And finally, and possibly most obviously, the presence of nitrate, because you need nitrate in order to have the process of denitrification occur. While denitrification is often considered the dominant form of nitrate reduction, there are multiple other processes that play crucial roles in our ecosystems. Assimilatory and dissimilatory nitrate reduction convert nitrate to ammonium, recycling biologically available nitrogen in the system for assimilation by organisms or release into the environment. It is important to emphasize the differences between the two processes. Assimilatory reduction converts the nitrogen into biomass, whereas dissimilatory reduction uses nitrogen as an electron acceptor, not incorporating ammonium into organic matter. The type of reduction determines the regulators of these reactions. Assimilatory reduction is determined by the presence of ammonium. As the levels increase, the effectiveness of reducing microbes to compete with other organisms is reduced. Much like the nitrogen-fixing microbes, the process of reduction takes energy that is completely unnecessary in the presence of the resources it is working so hard to harvest. This process occurs primarily in aerobic soils, where nitrate will be available. Temperature also has a positive effect on assimilatory reduction. Dissimilatory nitrate reduction does best in anoxic environments with relatively low nitrate levels. Emphasis on relatively low. The dissimilatory nitrate reduction reaction is more efficient at capturing nitrate, but not as energetically effective. This means that they will be outcompeted by denitrifying microbes when nitrate is relatively high. Think of it like a cactus in a desert. It's very effective at capturing water, but cannot compete with other plants when water becomes more readily available. The exception to this limitation can be found in saltwater environments, where in some studies, dissimilatory nitrate reduction appears to become the dominant process. Finally, increasing temperature has a positive effect on dissimilatory nitrate reduction. The final part of the nitrogen cycle we will discuss is anaerobic ammonium oxidation, also known as anammox. Anammox is a process that simultaneously transforms nitrite, or NO2, and ammonium, NH4, into nitrogen gas. This process is used around the world to treat sewage, turning harmful levels of biologically available nitrogen into harmless nitrogen gas. Typically, the presence of ammonium, nitrite, and ammonia are important to this process, with ammonium and nitrite fueling the reaction and ammonia inhibiting anammox. Low levels of organic matter are optimal for anammox conditions due to the lithotrophic nature of most anammox microbes. Oxygen also inhibits anammox, so anaerobic conditions are best for these microbes. Interestingly, relatively colder temperatures of 15 degrees Celsius have been found to be optimal for anammox. At higher temperatures and organic matter levels, denitrifying bacteria divide faster and outcompete anammox microbes. And as the nitrogen we've followed since nitrogen fixation finally re-enters the atmosphere, we finish our lectures on the best known and possibly the most important processes in the nitrogen cycle. Now that we have covered the best known mechanisms of the nitrogen cycle, it's important to apply what we have learned to a living, breathing ecosystem. The nitrogen cycle behaves differently in every habitat. Today, we will discuss the nitrogen cycle in relation to seagrass communities. Let's first introduce the general characteristics of seagrass ecosystems in order to gain more insight into its interactions with nitrogen. Seagrasses are coastal organisms that are composed of three parts relevant to the nitrogen cycle: the water, the seagrass community itself, and the sediment they interact with. To start with, seagrass systems are oligotrophic, as in exist in low nutrient environments. This is reflected by the plant's nutrient ratios, what is required for growth, which is approximately 550 to 30 to 1 for carbon, nitrogen, and phosphorus, respectively. This is compared to the Redfield ratio of 106 to 16 to 1 that is observed for plankton or algae. This means that seagrasses are better adapted to lower nutrient environments than plankton. This is one of the reasons why seagrass has declined around the world. As our fertilizer inputs increase, the ratio of carbon to nitrogen and phosphorus is reduced. This allows algae to outcompete seagrasses as they can grow faster, smothering the bed and creating zones of reduced productivity and biodiversity. Another important detail is the primary form of nitrogen found and used in seagrass systems: ammonium. Ammonium is typically present in relatively large supply due to the hypoxic or anoxic conditions found in the sediment. This creates a microbial demand for oxidized nitrogen forms, and reactions like DNRA lead to the production of ammonium. Decomposition also releases ammonium through ammonification. Once released, ammonium can then diffuse into the nutrient-poor water column. Both the water and the sediment are potential areas of assimilation, as seagrass absorbs nitrogen through both shoots and roots. Seagrasses have also been found to prefer ammonium over nitrate, the other common form of nitrogen in marine environments. The effect of seagrasses on ammonium is dependent on the time of day. In the daytime, seagrass absorbs carbon dioxide and emits oxygen via photosynthesis, increasing pH and redox potential. This, combined with the increased assimilation of nutrients by seagrass, reduces the amount of available ammonium. At night, plants reduce their assimilation rates, emit carbon dioxide, and absorb oxygen, reducing pH and redox, and subsequently increasing ammonium. Another way seagrass alters the local nitrogen cycle is through its physical structure. The seagrass itself can slow currents, causing debris to settle and become sequestered in the sediment. This debris is known as allochthonous material, coming from outside the seagrass system. The seagrass bed also sequesters its own matter, like dead leaves, known as autochthonous material. Some of this material may remain here for a relatively short period of time, depending on oxygen and pH conditions, emitting reduced nitrogen forms via decomposition. However, a significant quantity will remain in a healthy bed for hundreds or even thousands of years. This process is often associated with sequestering carbon, but this matter also contains large quantities of nitrogen. It has been estimated that the nutrient cycling abilities of seagrass, including but not limited to sequestration, are worth $1.8 trillion a year around the world. The root system of the seagrass also significantly alters the sediment and subsequently nitrogen. Normally, marine sediments have a shallow oxic zone on the surface, quickly becoming anoxic with depth due to microbial activity. Roots introduce oxygen into the system, creating an oxic-anixic interface. This, combined with the emission of nutrients from seagrass, makes this area a popular site for nitrogen-fixing microbes. These organisms lie just outside the oxic zone, reducing oxidized sulfur forms like sulfate. The presence of these microbes in seagrass systems are several times that of adjacent sediments. The significance of this process for the seagrass system is highly dependent on the climate. Temperate systems have been found to produce only 6 to 12% of their nitrogen demand via nitrogen fixation, whereas tropical systems produce up to 50% of their nitrogen demand. This interface is also commonly the site of coupled nitrification-denitrification. The oxygenated zone produces nitrate via nitrification, and when the nitrate enters the anoxic zone, it becomes denitrified into atmospheric nitrogen. This is further stimulated by seagrass providing nutrients and reducing toxic sulfide levels. The dominance of this coupled process can be upset if the system is relatively nitrogen poor. During the day, the pH and plant demand for ammonium reduces nitrification. If the system is chronically nitrogen, specifically nitrate, poor, DNRA can then dominate, which increases ammonium concentrations. This in turn can stimulate anammox as the dominant process releasing nitrogen into the atmosphere. Typically, however, the aerobic nature of denitrifiers and the presence of sufficient levels of nitrogen mean that coupled nitrification-denitrification is the dominant pathway. Hopefully, the contents of this lesson have been effective at introducing you to the factors and relationships that shape the nitrogen cycle, with an example ecosystem that drives the point home. This is such an important facet of our world system, and is a key factor in the conservation and management of our planet.